Hello everyone, my name is James Fleming and I'm a postdoctoral researcher at the University of Oslo's Natural History Museum. I'm really excited that you came to my poster because I'm really excited to talk to you about what I've been working on for the past few months. nRCFV, a new normalised version of RCFV, Relative Composition Frequency Variability. RCFV has been used over the past 8 years as a measure of compositional heterogeneity in a number of different pernicious phylogenetic problems, including, but not limited to, the Lophotrocha spiralia problem, the Cnidaria ctenophora first problem, and the evolution of orb weaving within the spiders. RCFV measures the compositional heterogeneity in a dataset by providing a value from 0 to 1, with 1 indicating an incredibly heterogeneous dataset and 0 indicating a homogeneous dataset. Its child values, character state-specific RCFV and taxon-specific RCFV, measure how much a specific character state and taxon each contribute towards the total RCFV value. However, because RCFV measures relative change across a dataset in order to establish its metric of compositional heterogeneity, there is a concern that the size of the dataset may bias the size of RCFV itself. A single change within a small dataset is a larger relative change than a single change in a larger dataset. With this in mind, we employed a number of simulation datasets to see if that is true. As RCFV is often applied to single gene sequences within multi-gene datasets to compare between partitions, this is a very, very clear and present problem with the metric. So, using 10 random trees from 50 taxa to 500 taxa, and 10 amino acid and nucleotide lengths from 300 amino acids to 3000 amino acids, and 900 nucleotides to 9000 nucleotides, we created 20,000 simulation datasets. That is 10,000 amino acid datasets and 10,000 nucleotide datasets. And we then calculated the RCFV, the taxon-specific RCFV, and the character-specific RCFV values for each dataset. We generated these simulation datasets under the idea that they would show compositional homogeneity, because this would ensure that we should, in theory, get very, very similar or the same RCFV values across the board for all of our simulation datasets if variations in breadth and length of the dataset were not an issue. However, what we found was indeed what we suspected, that RCFV is biased by both the length and breadth of the dataset. In order to combat that, we then used linear regression models and adjusted R-squared values to establish normalizing constants for each of these datasets, and found something incredibly interesting. Not just was RCFV biased by the amino acid or nucleotide alignment length and by the number of taxa in the dataset, it was also biased by the number of character states within that dataset. And so different normalization constants were needed for both nucleotide data and amino acid data, because the number of possible changes from 4 states or from 20 states was affecting the calculation of RCFV. New normalized nRCFV is capable of between dataset comparisons, whether sequences are shorter or longer, and whether your dataset is highly populated or unpopulated, or whether it is nucleotide data or amino acid data. In addition, a side effect of these normalization constants is that no longer do the child values of RCFV, taxon-specific and character-specific nRCFV, tell you how much compositional heterogeneity is inside of that character or that taxon, rather than how much it is contributing to the total value. This allows you to compare these taxon against the total dataset RCFV using standard deviations, means, and other standard metrics. nRCFV is a fast, effective means of detecting compositional heterogeneity in your dataset that is now unbiased by the number of taxa and the number of positions present in the dataset. This new implementation allows for comparison between taxon and character-specific values and the whole dataset value, which can allow users to make informed decisions about viable recoding strategies and taxon exclusion, rather than merely informing you about whether or not a sequence is compositionally heterogeneous or not. nRCFV presents a new way to assess and compare compositional heterogeneity reliably within and between datasets, to evaluate which datasets are potentially more accurate or more likely to fall victim to common model issues. It's available in the newest version of Bacoca, which you can find at the QR code in the poster or at my GitHub. And I'd really love for you to just try it out on any problems that you have, and keep in touch and tell me how it goes. All right, thank you very much for listening.